Okay, next thing we need to look at is conceptual, and it is frame of reference. And so frame of reference should be somewhat familiar, even though you might have never called it frame of reference. So this depends on the person who is viewing or experiencing the motion. It is like the first person account of what is happening. So a good way to think about this is to think about two different people and saying goodbye on a train, okay? So the person on the train, they feel like they are standing still. Even though they are on something that is moving, they don't feel like they're specifically moving around. However, to the person standing on the side, it would look very much like they were moving, right? So it's different perceptions of how motion is experienced depending on where you are. It is your reference frame, okay? To examine this a little bit more, let's think about if you're standing on the side of the road and you see somebody throw something off of something, like off of a moving truck. So if the truck was at rest, you would see them just throw it like normal because you and the person on the truck have the same frame of reference. However, if the person is on a truck that's moving in the same direction that they're throwing the object, it might seem very odd. It might look like they can throw it really, really far because they're now throwing it plus the movement that was going with the truck. In the third scenario, if they're moving away from the direction that they throw it, to the person on the truck, it probably looks like they're still throwing the ball. But to you, it might look like the ball stayed still while they took off to the side because it would probably drop straight down. There's actually a very famous Mythbusters experiment where they do just this with an air cannon. I suggest you look it up on YouTube. It's a great video. Now, all of this comes into play with us because you're going to get questions on a test that looks something like this over here, where it's asking about these two different cars, right? So in these two different cars that are seen from above, it says both cars are traveling at the same speed in the same direction, so same velocity, right? How would the relative motion of car A appear to the person traveling in car B? Well, think about this. If you're riding on the highway and somebody is in the next lane going at the same speed, you can look out your window into theirs and it looks like they're just sitting still. So it's the whole idea that from your frame of reference, this frame of reference, if they're going the same speed, it's going to look like two people are just sitting side by side each other, right? So it's like they would be stopped. So this is where everything comes together. This is where your frame of reference and vectors of velocity and all of that, canceling each other out because of different directions, all come together to play. And this is an actual test question. Okay, so let's look at the question. The question says, the current of a river is flowing south at a speed of 10 kilometers per hour. The speedometer on the motorboat moving north indicates the speed of the boat to be 14 kilometers an hour. A person is traveling north on a bicycle along the riverbank. So same direction as the boat, right? But what they want to know is how fast must the bicycle rider travel so the boat and the bicycle appear to be moving the same speed or same velocity to the observer on the shore, which is right there, right? So take all of that in for a minute. The speedboat, its speedometer says it's going 14 kilometers an hour. However, it's on a river that we know is going in the opposite direction, south, at 10 kilometers an hour. Therefore, their vectors are different, and it's not going to be 14 kilometers an hour that they're traveling. So we would have to figure out what speed or velocity they're going in the boat to this observer on the shore. And there's a real easy way to do this. They're opposite direction vectors, so they're going to cancel out. So 14 kilometers an hour minus 10 gives us 4 kilometers an hour that the boat looks like it's going to the person on shore. So for them to match that on the bike, they also have to be going 4 kilometers an hour. And that's how that would do. But you have to take all of it into account. The vector addition, changing up the different vectors, and then the frame of reference. This person is watching that person go by at the same speed they think they're seeing that person go by, meaning they have to look like they're moving side by side. A lot more force is being put and effort is being brought out by the boat, but that's because it has to fight against the river. You probably do this all the time, you just don't think about it. But this is an example where you would have to work it out, and you'd have to eventually figure out that yes, this person has to be going at 4 kilometers an hour.